Let us spend our time revising question 6, which we know from the structure of our exams that it looks at chemical equilibrium. Always, before you begin physical sciences problems, in this case chemistry, the first thing that you do is that you interpret the problem. For us to interpret this problem, we'll firstly start by reading it. The problem reads as follows. The reaction of substance A, which is a gas, and substance B, which also is a gas, to form compound AB, which is a gas, is represented by the following balanced chemical equation. So we are told here that A reacts with B to form AB, and all of these substances are gases. We are further told that we will assume that this equation is actually balanced. Now, the other thing that we see is that we have here double arrows. These arrows would mean that this reaction is reversible. That means A will react with B, they will combine with each other and form a bond, resulting to a product of A and B. Along the way, as time goes on, A and B will decompose. That is, it will break into A and B. That means A and B will then break and go back to form the reactants we started with. So this reaction basically goes forward and reverse. We're going in this direction to form that, and we also go in this direction to actually form these two. We further are given that here the change in enthalpy is greater than 0. That is to say that this reaction is an endothermic reaction because our change in enthalpy is positive. So this means that this reaction absorbs energy. It requires energy for it to happen. So here we have some form of heat that is put into this chemical system, and the reaction then begins to happen. Additionally to what I've said, if you have a reversible reaction, there is a possibility that at some point it will reach equilibrium because we have reactions that are going forward and backward. The question continues to go on to say, the reaction reaches equilibrium at a constant temperature, T degrees Celsius. Now, when we reach a certain temperature, T degrees Celsius, our reaction reaches equilibrium. I mean, we expected that, as I said, that if you have a reversible reaction, there is a chance that at some point it will reach equilibrium. They say here the graph below shows the concentration of reactants and products against time versus time under various conditions. So now in this graph here, we are given the concentration of the reactant A and B and the product AB against time. This is plotted with time. So as the reaction progresses, we look at how those concentrations change, and we can see here that there's a lot of lines that represents the increase, decrease, or even remaining constant of the concentrations. Let us go through this diagram so that we are able to understand how the concentration change with time. Our reactant A begins with some concentration here, a higher concentration at this point, when the time is 0 seconds. And during that time, we also have some concentration of the reactant B. And of course, you can see here that the reactant AB is at 0. We don't have the reactant, the concentration of the product, because the reaction really is at the beginning. We haven't really started reacting the A and B. However, as the time goes on, if we start going on with time like that, we can see that A decreases maybe up to this point where we have some decreased concentration and the time there has increased from 0. And the same is true when you look at B. B has decreased and, we have some concentration here at the time there that has increased. I think that time there's about 5 seconds. And during the very same time of 5 seconds, we can see that AB, the product, has increased. We have some concentration. It moved from 0 to some concentration. That means now A and B are actually reacting to form AB. So that means they will decrease in concentration. So when they decrease in their concentration, we see an increase in the concentration of the product. So this means that these two, as they react, they get used up, so they get smaller, and AB starts emerging. It comes out as a product. And this decrease between A and B will continue until some point where we are here at 10 seconds. And the B will also increase to that point. However, during this time frame here, along the way here, we will start seeing the reaction going backwards, meaning the AB will break apart and form back the A and the B because it's a reversible reaction. And then, at some point here, as this reaction is progressing, we're having these two reactions taking place at the same time. A reacting with B to form AB, and AB breaking apart, decomposing to form A and B. This will continue to happen like that until we reach this point here, where we see that when we are at this point, the concentrations of A, B, and C do not change anymore. So if you look at the concentration here, let's say of A, it gives me that number of 15 here. And if you look at the concentration of B, it gives me that number, 0.15. So that is 0.15. This is 0.1, not 15. And when we are somewhere here, we then have 0.05. But as the time continue to go on, let's say we are at this point, we get the same numbers of the concentration. They haven't changed. And this will continue to be like that until such a time we are here at 30 seconds. Now, during this time frame here, we say that the reaction has reached dynamic equilibrium. In other words, our concentrations are constant and the rate of the forward reaction is the same as the rate of the reverse reaction. Remember, we're having two reactions occurring at the time here. A reacting with B to form AB, and AB breaking apart to go back and form A and B. So those reactions are occurring since here, and they'll continue to occur at the same time here. But at this stage here, they occur at the same rate, and we say that is dynamic equilibrium. Now we see here at 30 seconds that the reactant B spikes and increases suddenly to a higher concentration there. This means that we have increased the concentration of AB. Imagine this as if you are having a beaker here, and then you have, your A and B reacting to form AB and AB going backwards to form A and B. And then you pour in some more of B in here. The concentration will suddenly change and become higher. This is what is happening at this stage here. So if you see a spike, it means it was an increase in concentration of B. However, we know from Chatellier's principle that if we have a change in dynamic equilibrium, if we have a disturbance in dynamic equilibrium, which is what is happening here, we are disturbing dynamic equilibrium. Chatelier discovered that that disturbance must be cancelled, it must be opposed, and that's how we're going to establish a new equilibrium. This is the reason why this increase here is actually decreasing, it's going backwards. The B is decreasing because we're trying to cancel this increase that we had here. Now for B to go backwards, it means that it must react with A. If B decreases, it means it's reacting with A. Both of them must decrease because they are reactants. Remember, if B decreases, it means it's reacting with A. So they're getting used up. And when they decrease, it means AB must increase. And this is what is happening here. You will see that B decreases and A also decreases. And the AB then increases, it gets formed. And at some point, as that is happening, you will find that we will reach new dynamic equilibrium. We establish a new dynamic equilibrium. Now, grade 12, listen to me very carefully here. When we reach new equilibrium, we establish new equilibrium. The equilibrium constant Kc that we're going to have here, the Kc here, will be the same as the Kc we're going to get here. So if I have a Kc of 2 here, I also should get 2 here. And this happens if the change was caused by an increase in concentration or even a decrease in concentration. So if you change the concentration, we will establish a new equilibrium, but this new equilibrium will be the same as the previous equilibrium. Now, when we get to some point here, let's say 55, I think, we can see that we start having changes again here. Our reactant A increases and our reactant B also increases, and the product decreases. So this tells us that there is a form of change here. It's either we change the temperature or the pressure, but it is difficult to tell which one by just observing those lines. Now, what is happening here is that you will see that if A and B increase, so we're having an increase in A and an increase in B, this means that these two are being formed. So this means AB is actually breaking apart. It is decomposing, it is decreasing, and it then goes in that direction to form A and B. So it means we're having a reverse reaction at this point here. We're going backwards. We're having a reverse. We are favoring the reverse reaction. We're having more of the product of the reactants than the products. And of course, whatever change that took place here, whether the change in temperature or pressure, will be cancelled, so that when this decreases and this 2 increases, we establish a new equilibrium. And again, here there's a twist. If the change was caused by the pressure, the change in pressure or the change in volume, the equilibrium constant Kc will be the same as here, and here we'll have the same Kc. If the Kc is 2 here, it will also be 2 and also be 2 here. However, you must note that if the equilibrium was changed by changing the temperature, our Kc won't be the same as the 2 that we can find here. If, let's say, the Kc was 2 in these two previous equilibrium constants, then the Kc here won't be the same. It will be a different Kc. This happens only when the change was caused by temperature. Now, I am done with interpreting this question, and I am ready now to classify this question. I will classify this question as a question that requires the knowledge of chemical equilibrium, and my questions will be based around chemical equilibrium. And of course, chemical equilibrium is linked to the rate of reaction, so we could get a mix of those questions in here. That's what I should expect. Then the next stage that I'm going to do is really going to answer the question. For me to answer this question, I really go straight to the questions and answer them. The first question says to us here, 6.1, define the term reversible reaction. I think in my interpretation already I spoke about reversible reaction. It makes sense for the examiner to ask me this question because, that beautiful diagram speaks to that. So a reversible reaction, really, we know that is a reaction that can proceed in both the forward and reverse direction. I think this question, usually they mark it out of 1, but I made it 2 here. And you know, the last thing that you do when you answer questions is that you navigate the answers. In other words, if I'm looking at the step-by-step that I'm following here, we are navigating the answer. Now, to navigate simply means that you quickly go through your answer and see that you didn't make errors, you didn't make mistake, and everything makes sense. So if you're doing a conceptual question like this, where you are writing and not doing calculations, check for spelling errors, you know, and all that, the grammar, if it's correct, and all those things. Now, the next question then, 6.2, says define the term dynamic equilibrium. Again, we spoke about dynamic equilibrium when we did our interpretation. It also makes sense to get this type of a question here. These are the things that you see in the question. So dynamic equilibrium really is a point at which the rate of the reverse reaction equals, or you can say is the same as the rate of the forward reaction. And this will definitely give you 2 marks. And remember, always take your time to navigate your answers. Check if you don't have any spelling errors, if everything is written properly, if your grammar is sitting out properly. Going to the next question, 6.3. It says here, which reaction proceeds faster in the time interval? They say here, write only equilibrium, forward, or reverse reaction. So we want to see in the given time intervals here, which reaction is actually proceeding faster, which is faster. Remember, I said here that as these reactions are taking place, there is both forward and reverse reactions taking place. And we know that at some point here we reach equilibrium. So, you know, they're asking us to check for that on the intervals that we're given. The first interval that we are being given is from 0 to 10. So we are looking at the time here to here. So that means we are looking at this part of the graph. We want to see here which one between the reverse and the forward reaction is happening faster, or if really there is equilibrium here at this point. Now, obviously, you can see that this part here, there is no equilibrium because AB is decreasing and AB is being formed, is increasing. And at some point, I said when we are somewhere at some point here, AB will break apart to form A and B. So it becomes a reversible reaction. So between that forward and reverse reaction, which one is fast? To find the reaction that is occurring fast, we can just look at the slope of our curves. If you look at the slope of this curve here, the AB is actually having a positive slope. What I mean by that is that if we were to draw a tangent or different tangents on this curve, you will see that all these tangents here, they actually have a positive slope. And we know that if you have a positive slope, it means that we are increasing. We are having an increasing graph or an increasing function because our slope here is positive. The gradient is positive. But if you look at the two curves here, the A and the B, you can see that they have a negative slope. If we draw a tangent here and a tangent here, all of them have a negative slope. And that tells you that they are decreasing. They are actually decreasing at a slower rate. And also the same is true if you draw the tangent on B. You'll see that all these tangents actually have a negative gradient as well. And that implies that they are actually happening at a slower rate. So we are forming AB faster than we are actually decreasing A and B separately. we are actually having a reaction where the forward reaction is happening faster than the reverse reaction. So my answer here would be that the forward reaction. Now when we get to 6.3.2, between the intervals of 10 to 13, which reaction is happening fast, the reverse or the forward reaction? Well, obviously we know that at this point we have dynamic equilibrium, and even from the definition of equilibrium, we know that the forward and the reverse reactions are actually occurring at the same rate. So that means here we are going to simply say we have actually equilibrium. Both reactions, forward and reverse, are occurring at the same time. Each of these answers will really give you 1 mark. But we have to check here. They say that explain your answer for this one of equilibrium. Well, I think I've just said it in words now when I was talking here. But to explain this really, we will say here that the concentration of the reactants and products remain constant. You know that the fact that the reactants and the products have a constant concentration means that if you plug them in on the formula of Kc, you'll get a value that doesn't change. So during this time, if you take maybe the concentrations at this point and you put them in the value of Kc, and also you take them here and put the value of Kc, you'll get the same number. So that tells you that the Kc doesn't change. It remains the same. So that's why the forward and reverse reaction are actually occurring at the same rate. And hence we call that equilibrium. Now when we go to, and of course, with this one, you'll get an additional mark. That's why this one is 2 marks here, because they give you 1 mark for answering that and also explaining them. Now looking on the next question, which is 6.4, we are required to calculate the equilibrium constant at t is equals to 15. So now we are mapping out here, t is equals to 15 would be somewhere here. We want the equilibrium constant at this stage. Now we know that our product will be measured here. So I'm going to write down my formula of Kc, which is given by Kc is equals to the concentration of AB. Remember, AB are the products. And if you look at this equation that we have, they said to us that it is balanced. So I don't need to put any stoichiometric ratios on this equation. And I'm dealing with only gases. It means all of these substances will be included in the Kc equation. Now it means at the bottom here, I'm going to divide by A, concentration of A and concentration of B, the product of the two. And I'm saying that AB is measured here as 0.1. So I'm going to plug in here 0.1. And the concentration of A, if we look at the concentration of A here, it will be measured as 0.15. And the concentration of B will be measured to be 0.05. And from here, this question becomes very, very, very boring, because we're just going to put everything on our calculator and allow the calculator to do the magic for us. And we get a number here of 13.33. Remember that Kc is unitless. It only tells us whether we are favoring the forward or the reverse reaction. And of course, here you can see that our number is much, much more bigger than 1. And this would mean that we are favoring the forward reaction. It means we are forming more of the products then we are forming more of the reactants. Remember, both reactions are occurring at the same time. This is the reason why we call equilibrium dynamic equilibrium, because these reactions are still happening. They are moving, they are dynamic, except that we are forming more products than we are forming reactants. So this question here is really 4 marks for free, 1 for the correct formula. Remember, this formula is not there on the formula sheet. 2 for correct substitution in the numerator and denominator, and 1 for the final answer. Now, when we look at the next question, we are told here in 6.5 that a change was made to the equilibrium of the chemical system at t is equals to 30 seconds. Now, if we look at this, we spoke about this change when we did our interpretation. We know that that change is caused by concentration, an increase in concentration. Now, the question then further goes on to say 6.5.1, state Le Chatelier's principle. Le Chatelier's principle says that when a chemical system at equilibrium is disturbed, the system shifts in the direction that minimizes or cancels the disturbance. So Le Chatelier's principle says that when we have a chemical equilibrium that is being disturbed, the system will move in such a way that it cancels or it minimizes that disturbance, and we go back to a new equilibrium. We establish a new equilibrium. I mean, we've seen that in our graph when we interpreted our graph. And to write this down would really be for 2 marks. Then the next question says to us here that write down the change that was made at t equals to 30 seconds. We know that this change was the increase in the concentration of substance B. So I'm saying here the concentration of B was increased. Remember, we are at this part here just to be sure that we are following each other. We are here. We spoke about this when we did our interpretation. And this is why it's important to interpret problems before you answer them, because already you build up answers, really. And it makes the question easy to follow also what you are being examined. Now, the next question says here, use Le Chatelier's principle to explain how the system will respond to the change. So now this change, you spoke about it to say, according to Le Chatelier's principle, we'll have to then, deal with this increase by cancelling it, by decreasing the very same increase. And in that sense, we'll then reestablish a new equilibrium. So that's what we're going to really explain here. We are going to say here, when we put it in words, the increase in the concentration of substance B favors the reaction that decreases the concentration of B. what I've just written down here, really, I'm saying that the increase in B will favor a reaction that will cause a decrease in the substance of B. Because we've increased this, we have to cancel this increase by decreasing it. It's like it's the opposite. That's what Chatellier's principle is saying, really. Then by doing so, you can see that what is going to happen. If we decrease B, and as I said in my interpretation, if we decrease B, it means it's going to react with A. Then the two will be used up. They will both decrease. And when these two decrease, it means they are forming AB. Then AB would increase. That's why these two are going down and the product AB has been formed is increasing. So in that sense, I am then going to conclude to say here, thus the forward reaction is favored. I hope you are able to see that if we decrease B here, it means that the B is being decreased. A must also decrease because they both are going to react. So they're going to be used up. And when they get used up, they basically are forming AB. And all this process is doing really is favoring the forward reaction. It means we are going in that direction. We are taking A and B to form AB. So on the two reactions that are occurring, we are forming more of the products again here. So that's what I'm saying in this question. And we are going to get marked for 2 points because you'll get 1 mark here and another mark there for that last statement to conclude on your last statement. Now let us jump to the next question, which then says to us here 6.5.4, which physical condition has been kept constant? Now you must be able to see that when we make the changes of concentration here and everything up until this point, we must keep the temperature constant in this whole process, because if you change the temperature, our reactants and product will behave differently. So the answer for this is that temperature is the one that was kept constant. So all the time when you change concentration, the temperature must be constant. And also when you change the volume, the temperature must also be constant. And this really would be for 1 mark. Now, if we then move to the next question, it says here that the new equilibrium of the chemical system is further disturbed at T is equals to 55. Let us look at that. We spoke about this. You can see that here we'll have a new equilibrium to this equilibrium here. But this very new equilibrium gets disturbed at this point here when we are at 55 here. It gets disturbed, and I said here we are not sure which one is it between temperature and pressure because it's not easy for us to tell. One of the ways really to tell is to calculate the equilibrium constant and compare it. So in this question, they then say to us, use calculations to determine the change that was made at 55. And again, as I said, if we calculate the equilibrium constant and compare it with the previous equilibria, we'll be able to tell which change took place. Now here I'm going to then calculate my Kc. I'm doing 6.6 and I'm saying Kc will still be defined by A, B because we still have the same reaction. Then I'm having A here over the concentration of B. But now here we're going to read our numbers from the graph. So if you come here where we establish new equilibrium, remember the new equilibrium would be anywhere on this time frame. So I can take any time frame here. Now if I take, let's say 70 seconds here, and I look at the concentration of AB, which is this one here, I'm reading here 0.12. So it means I'm going to have 0.12 And if I take that of A, it's here. I'm reading again here 0.1. And if we look at the concentration of B, I'm reading 0.2. And when we pull our calculator, we really have an answer of 6. And again, you can see that this number is much more greater than 1. And it tells you again that we're still favoring the forward reaction. That means we're forming more products than reactants. The reverse reaction really, in this case, we are forming less of the reactants. Now, let us interpret this number. If you look at this number here, you can see that it's a 6. And in the previous equilibrium, when we are here and here, we got an equilibrium of 13.33, if you remember that number. So you can see that the Kc is not the same. So this means that the change that took place must be temperature, because with pressure and volume, we should get the same Kc value. Now it means here I'm going to then answer the question. I'm going to determine that factor. I'll say here, since the newly established equilibrium, which equilibrium am I referring to? I'm referring to this equilibrium here. Remember that after this disturbance, we are going to cancel this disturbance and establish a new equilibrium here. So this newly formed equilibrium here, that's what I'm saying, is not the same equilibrium Therefore, the disturbance to equilibrium was caused by the change in temperature. This was caused by the change in temperature, and this is really out of 6 marks. And you can see where the 6 marks really will come from, because you're doing a lot of analysis here. 1 mark for the formula, 1 mark for correct substitution at the numerator and denominator, 1 mark for the correct final answer. So we're having 4 there, and we get 2 marks for your explanation. Now you should also always navigate, as I said, and if I'm navigating this, I'm saying that since the newly established equilibrium. So here I see that I need to improve by saying the equilibrium constant, meaning the Kc value, the equilibrium constant is not the same as the previous. It's not the same as the previous. So guys, that's why it's important to navigate the previous equilibrium constant. So here I have to also add constant. So you just have to say the newly established equilibrium constant, Kc, is not the same as the previous equilibrium constant. Therefore, the disturbance to equilibrium was caused by the change in temperature. So please fix that. You should write your answers correctly for you to get the full marks. So it's the Kc that is not the same here, not just the equilibrium, but the Kc. Now, if we go to the next question, they say here, was the temperature increased, decreased, or remained the same? Now we said here that the equilibrium is disturbed by changing the temperature. But how did the temperature change? Did it increase, decrease, or remain the same? Obviously it didn't remain the same. We know from calculating the Kc value here that we changed the temperature, so it didn't remain the same. But the thing is, we have to determine if it was increased or decreased. Now to do that, you must be able to see that this reaction from this path going backwards here, we actually had a constant temperature. And also this reaction was endothermic reaction. In other words, I said here we are having A reacting with B to form AB, and AB goes back to form A and B. But I said this is an endothermic reaction. In other words, we have heat here. So we are treating heat as a reactant. Now, this graph tells us that the reverse reaction is favored because we're saying that the product is actually decreasing. Our AB is decreasing and our A and B are actually increasing. So what am I saying? I'm saying AB is decreasing, is going down. So for it to go down in concentration, it means it's breaking apart here to form A and B. It's going in that direction. So our reverse reaction here is taking place. And by doing so, we actually establish new equilibrium. There will be a point where we go to the initial conditions. Now, if in this reaction I'm saying that we are favoring the reverse reaction, we are actually forming A and B. And because it's an endothermic reaction, it means we are also forming heat. We are increasing the heat. So for us to increase the heat, it means originally when we disturbed equilibrium here, we decreased the temperature. Because if we decrease this temperature here, if I drop the temperature, if I decrease the temperature in the original equilibrium, so at this equilibrium here, if I decrease the temperature, the heat here will be smaller and the equilibrium will be disturbed. So for me to go back to equilibrium, according to Chatellier's principle, I have to cancel that effect. It means I must increase it. I must increase this temperature. So to increase the temperature, it means I have to break A and B. And by breaking it, it means we are doing a reverse reaction. We are forming A and B because when it breaks, I'm going to have A and B, and it's a reverse reaction, and we form heat. That means the heat increases to then cancel this effect of decreasing it. So it means initially we decreased the temperature here. It means to answer our question, the temperature was decreased. The temperature was decreased. So the answer to this question really would be that we say the temperature was decreased, and really you are going to get 1 mark for this. And 6.6.3 says which physical condition was kept constant. Now we are at this part of the question here. Remember, in this direction, the temperature is constant here. Then we are saying here, when we change the temperature, because the temperature is not constant anymore here, we've changed the temperature here and established a new equilibrium. So which physical condition was the same? It was constant. Now, when we change the temperature, always the volume or the pressure must be constant. So it means here the volume, or you can say the pressure, must be constant.